Okay, good morning, Astronomy 1010. Welcome to our final week of lecture. This week we'll be focusing on the Jovian worlds and the Jovian moons, which are a particularly fun topic. Oh, jeez. My lab is printing as we speak, and it's spilling out of my projector all over the floor. So I might have to do a couple of emergency operations here. Sorry. So our lab today hopefully will be the massive Jupiter lab. And I was just telling students before I started the recording that I'm a little concerned that Flash is no longer being supported. And I believe the application that we're running today is a simulation of observations of Jovian moons. The CLIA homepage is here if you want to follow along. But as usual, you guys can just kind of watch me do the lab and take the data with me. There will be some data to take. I'm hoping to share screen, and it's called The Revolutions of the Moons of Jupiter. Let's see if this, oh boy. Oh, wow. Okay, it looks like, oh, bloody hell. Oh, okay. What is the year today? It's 2020. How could I forget that? And
it's Pearl Harbor Day.
12/7. Is it Pearl Harbor Day?
Yes.
Oh my gosh.
79 years ago.
Fudge. I am deeply concerned.
Wow.
Huh. That is
Technology has not been your friend the last month.
no, not really. I'm trying to think of why. Maybe, you know what? Maybe I need to run this as administrator. Can I do that? If that makes a difference. Nuts. I don't know what we're going to do. Okay, we'll deal with that later. Let's have our lecture, and then during tea break, I will attempt to figure something out. Okay. Anyways, we'll see what happens when we get there. What's the last note that you guys have? I know we did the sort of composition of the Jovian planets. Let me adjust my glare here. I don't have stuff on the screen. What do you guys have for your last bit of intel?
Frost line.
Sorry?
Frost line.
Oh, we calculated the frost line. Very good. What's the idea behind, thank you, Ava. What's the deal behind the frost line? Let's make sure you guys remember the big takeaway.
Allowing massive Jovian planets to form when capture hydrogen, helium gas.
Okay, so hold on a second. Let me share a screen with y'all. It does explain why the Jovians formed at the outer edge of the solar system. Who can kind of explain it to me in a nutshell? What's the idea? What's the concept? Surely someone understands what I was talking about for the last 20 minutes of class last week.
So as the planets were forming, or even now with their rotation, it attracts certain particles or like rock elements into the planet.
Okay, kind of, yeah. That's groping towards goodness. What is the frost line? What does the line demarcate? What does it separate? Hey, suppose your little brother asked you at Christmas dinner, why did the Jovians all form far from the sun? Could you answer that? They say, hey, Frank, hey, Cam, you're taking an astronomy class, so you know some things now, right? Why did all the Jovians form so far from the sun? What would you tell your kid brother? Would you go, Would you say that to them, or would you want to have something intelligent to say about that?
Something
I would have to say, like, since they're probably far away, they're not getting as much sunlight as like the other planets near the sun. So it's
Okay, so it does have to do with you're not getting as much sunlight, so it's colder out there. So then how does the cold lead to the formation of Jovians?
because it's mostly of gas.
Wait, what is it?
The
What is-
Jovians.
Oh,
Yeah, the
but
Jovian
normally hot things are gas and cold things are solid. So that's a little weird, right, Frank?
Yeah.
So with their distance from the sun, the frost line is where, like, the hydrogen, the H ices transition from gas to
Hydrogen is always a gas.
solid.
Well, today we'll see that hydrogen is not always a gas, but usually hydrogen is very volatile. I need to turn my heat down. Hold on. Is there no student out there who can understand what I mean? No one? Something changes interior to the frost line to exterior of the frost line, and it does have to do with gas, but it's not hydrogen.
It's helium.
Nope, it's not helium either. Helium's usually in a gaseous state.
Water.
Okay, yeah, that's why they call it the frost line, not the helium line or the hydrogen line. What do you think, Noah? You just joining us? Good morning.
Yeah, good morning.
I don't know if you got to watch the video last time, but the frost line is a concept. I talked about it for like almost a half an hour.
Yeah, like 3AU about, right?
Yeah, what happens interior to 3AU versus exterior to 3AU?
You have the terrestrial planets.
Yeah, okay, so why? Why are the terrestrial planets forming in here, but the Jovians are forming out here? I'm trying to understand that myself. That's a little confusing.
I think it has something to do with ice. I'm not
It has
entirely sure.
everything to do with ice. Where can ice isn't always ice, is it? Sometimes ice is like not ice. Isn't that funny? Because ice is H2O. And while all ice is H2O, not all H2O is ice. Ain't that the truth? Sometimes H2O is in the form of water, but not in space because there's no water in space. There's no liquids in space. So in space, you're either ice or you're gas, right? Where will the ice be gas? Where will the ice be solid?
This will be
Oh, outside the frost line.
Outside the frost line. Keep going, Andrew. Say something that I can understand.
It'd be outside the frost line because inside the frost line would be warmer for it to be frost, because frost is a gas, right?
It'll be a gas in here, right?
Yeah.
But after 3AU, your H2O will take the form of ice grains. So why do ice grains help Jovians form? This is kind of an important idea.
Probably like the composition of the planet, like
Well,
the
it's
water.
not a planet. It has to form to become a planet. What is it before it forms?
on a test measure.
A what? Before a planet forms, it's something called a planetesimal.
That's
a
what I was
lump.
trying to say. Yeah.
It's a protoplanet. It's a planetesimal. It's a lump that will become a planet. So how do I get terrestrial planets versus Jovian planets then? Wow, you guys totally didn't understand that, huh? I thought
Jovians start out as ice, and terrestrials start out as rock.
the frost line at 3 AU, and this is in the proto-solar nebula, but oh wow. Guys, sorry, we use Zoom for something this weekend, and we have the mirror set up. I can't read my own notes. At 3 AU in the proto-solar nebula, H2O goes from gas to ice. Now, remember that there are 4 sort of ingredients in the proto-solar nebula that can make planets. All right, you should all write this down because this fact escaped y'all. The 4 ingredients are 1, hydrogen and helium gas, and that's like 98% of the whole shebang. All right. 2, there are ices or H2O or hydrogen ices, and that's maybe 1%. And then there are rocks, rocky stuff. That's like maybe 0.5%. And there are metals. And that's like maybe 0.5%. These numbers are approximate.
Is that proto-solar? Oh, it's proto.
Yeah, proto-solar nebula. Sorry, I was writing kind of quickly here. So these two, in the inner solar system, these two are solid grains always in the inner or outer solar system. So terrestrials can form from these two, but Jovians get to form from 3 because far from the sun, wow, I'm having some spelling issues. Far from the sun, 3 of these are in a solid phase. This is always gas, okay? This is always in the gaseous state. What happens to the Jovians is they start swelling to basically double the normal size. For every 1 pound of rock and metal, you've got 2 pounds of rock, metal, and ice for Jovians. So because the Jovian planetesimals are much larger, so let's draw the picture, okay? So here's some rocks, and here's some metals, and that's your terrestrial planetesimal. Here's some metals and some rocks, right? But now you can add in some ices. And that means the Jovian planetesimals swell to much larger sizes than their terrestrial counterparts. Eventually so much that they can actually pull some gas from the protosolar nebula, and they can start absorbing the hydrogen and helium and holding it down by their gravity. This allows the Jovians to swell to immense masses, almost star-like masses, because they had double the amount of solid matter to begin with. That was why Jovians form far from the sun. That's the concept of the frost line. I think that's very interesting. Now, when your kid brother asks you why Jupiter and Saturn are so much bigger than the terrestrial planets, you can say, that's easy, little Jimmy. It's because of the frost line. And you can explain that to them if you feel like, you know, entertaining them, shall we say. Okay. One of the reasons we have lots of great images of Jupiter and Saturn, but maybe not so many modern pictures of Uranus and Neptune, has to do with the history of the space exploration of these Jovian planets. Basically, the Jovians for centuries, for millennia even, have been observed by humans as bright dots on the sky. For instance, right now, both Jupiter and Saturn are up in your local sky. Did you guys know that? You can see
Yep.
them with your naked eye. And do you guys know that something special is happening next week on the or a week or two from now on the 21st? Let's just check the calendar
Yep.
here. 2 weeks from today, I'm making the announcement here. Jupiter and Saturn will appear roughly I think it's an arc minute away from each other. And that's closer in angular separation than your eye can perceive. So basically, Jupiter and Saturn together are going to look like a superstar on your sky. Very, very bright star. And if you have a small telescope like I do, you can set that beast up and you can look through it, and you should be able to see Jupiter and Saturn in the same field of view. That will be pretty special. There's a nice, I think the Washington Post had an article on it this weekend. If you guys want to read more about it, Wash Post, Jupiter, Saturn.
Like a telescope, do you need to see it?
Even a very small telescope should be able to see the rings of Saturn. Copy link address. So we should see, oh, darn it, I'm past the paywall here. Hopefully you guys aren't. So I'll put that into the chat log. You should be able to find it in many other publications too that are completely free. So
I can't see the bottom of the board. All right, I got that.
all right, okay. So the earliest explorations, they were basically just dots in the sky. Of course, Galileo resolved Jupiter as a disk and could see the 4 Galilean moons. And with telescopes, we could see rings in Saturn, and we studied them that way for hundreds of years. Eventually, the Voyager missions, let's see if we can get the orbits of the Voyager missions. They were the first spacecraft to fly past the Jovians, and you really got to hand it to these engineers. They did sort of a remarkable thing. Let's look at the dates of these Voyager missions. So Voyager 1 did the first flyby. It was launched in 77, I think. And hold on a second here. Control plus.
Brandon, I just posted a link about the Jupiter and Saturn
Thank you.
thing.
So they actually got the mission to fly past Jupiter in 1979 and to fly close to Saturn in 1980. Those were the first ever really up close and personal pictures of the Jovians that we ever got to see. Now, you got to think about how amazing this is. They called this the grand tour of the solar system. Voyager 2 launched in 77, and the alignment of the planets was such that the spacecraft could slingshot first off of Jupiter, then Saturn, then Uranus, and then Neptune. Basically, that one space mission hit all four Jovian planets, which is incredible.
Nice.
In later years, we've sent more modern spacecraft to Jupiter. In the 1990s, I'll show you a picture. We sent the Galileo, in the 90s, we sent the Galileo mission to Jupiter, and we have some amazing high-resolution images to show you from that mission. In the 2000s, we sent Cassini to Saturn, and so we have amazing photos of Saturn. But you'll notice when I show you images from Neptune and Uranus, they're a little more old-fashioned because still today, we only have the up-close personal pictures from Voyager 2. Those are still like the best images we have of Neptune and Uranus. So we have not had a modern space mission go to those Jovians and get us some newfangled high-resolution images. It would be very nice to see that happen. The Galileo mission is going to figure heavily in our lecture today. Galileo spacecraft. Let's see if we can just check out the wiki page on it. I like showing students pictures of the spacecraft in the clean room. I think that's interesting. Come on, you stupid internet. There we go. Okay. So the Galileo spacecraft was impressive because it had this mothership, and they basically dropped a little suicide kamikaze probe down into the cloud tops of Jupiter on a suicide mission to measure the composition of Jupiter's atmosphere. I wanted to show you a picture. Usually they have an image, yeah. Here's the NASA clean room with the Galileo spacecraft in it. I don't believe you can see the probe in here. I'm not sure. I don't see that. It was kind of cone shaped. In any case, we have some very iconic images from the Galileo space mission. Probably one of the most famous are the rings of Jupiter. Galileo, seen from behind Jupiter. I've shown you this picture before. The spacecraft, because it flew behind Jupiter, was able to image Jupiter's very faint ring system. Boy, I'm having a slow internet day here. And brought back this kind of legendary photo of basically an eclipse of the sun from Jupiter's perspective. You can see sunlight filtering into the cloud tops, and you can see sunlight forward scattering off of the microscopic dust grains that make up Jupiter's rings. This picture is impossible to obtain from Earth. You have to actually get behind Jupiter in order to see it. The other mission, of course, was the Cassini spacecraft. That went to Saturn. It also had a small probe that landed on its moon Titan. I'll show you a picture of that later. And Cassini brought back just amazing high-resolution images of Saturn's cloud tops, ring system, and moon systems. And some of my best photographs. Here's the small moon Phoebe. And just, you know, look how close the spacecraft has gotten to those moons. And you can just see the violence that's this thing has been subjected to over the course of its 5 billion year history. So there's lots of nice photos to show you from the Cassini mission. Okay, so what do we talk about when we talk about Jovian planets? Let's go to our slideshows and see if we can't make some use of that and really get into it here today. Oof. Okay. So as you guys remember, these planets are big, but another thing to keep in mind is they also rotate extremely rapidly. I don't know if they show you the rotation rates here, but Jupiter rotates in about 10 hours, Saturn about 11 hours, and Uranus and Neptune maybe 13 to 14 hours, something like that. These things all rotate in approximately half of a day. And they're traveling at immense velocities. This tends to actually distort the shape of the planet itself from a perfect sphere into something called an oblate spheroid. They bulge a little bit at their equators and they're contracted a little bit at the North and South Pole. In fact, it turns out that a planet like Jupiter is probably, because it's a gas ball, it's about as big as a planet could possibly get. And I want you guys to look at this picture here. Because these planets are made out of gas, they're essentially bound by gravity and they maintain hydrostatic equilibrium like the sun does. Now, you probably forgot what hydrostatic equilibrium is, but it's a balance between the internal gravity of the planet versus the thermal pressure that wants to puff it out into a ball. The book makes an analogy that it's kind of like stacking a bunch of pillows up. If you stack a bunch of pillows, at first when you got 2 or 3 pillows, they're kind of big and fluffy. But after you stack enough pillows high enough on top of each other, the weight of the pillows will start to actually crunch them down a little bit. And you can see from this graph over here that at 1 Jupiter mass, you'll get a planet about the size of Jupiter. Remember, it has a radius of about 70,000 kilometers or so. At 3 times Jupiter's mass, you'd probably raise your radius to just a little bit above Jupiter. But if you start going upwards of 10 Jovian masses, you actually start scrunching the planet back down. So if a planet had more than 10 times Jupiter's mass, it would actually get smaller in radius, not bigger. Got a thought question for the class? Something to provoke you to get your noodles cooking this morning. The sun clearly has more mass than Jupiter, but the sun is bigger in radius than Jupiter. Why? If what I just told you is true, If as a planet gets bigger than Jupiter, its gravity will crunch it back down again. Why would the sun not obey that rule? Why does the sun actually have a radius that's 10 times that of Jupiter? There's a simple answer to this. I just wanted to see if you guys could. Jake?
It's a star. I mean, for a start.
Yeah, okay, so that is the correct answer, but flush that out. So it's a star, so what?
Oh, all the planets go around
Doesn't
it,
have the
right?
same structure as.
Structure might not be the best word, but you're kind of getting there, you know.
Composition and the fact that it's,
No, Jupiter and the sun have the same composition.
oh, okay.
98% hydrogen, helium, 2% other shit.
Maybe it has to do with the way that they were created, or the way that they were made.
They all came from the same pancake batter in the protosolar nebula. It's a star is the best answer I've gotten so far. The sun and Jupiter are the same, except the sun has something that Jupiter doesn't. What is it?
Heat.
Magnetic
Fusion.
fields.
No, they both have magnetic fields. They both have a
Fusion.
fusion. A star is a ball with fusion. A planet is a ball without fusion. So the fusion generates so much internal heat that it puffs out the star well beyond the planet's radius. Jupiter is a star with no fusion. It's a ball of gas with no fusion. And because of that, there's not enough internal heat to keep puffing out the radius of the star. If you add more matter, you squeeze the planet. Okay? Densities of Jovians typically turn out to be close to 1 gram per cubic centimeter, close to water, but they are by no means made of water. Let's take a look at the internal structure, what we believe the interior of Jupiter is like. And this is something worth taking notes on. This diagram, this lovely illustration, shows Jupiter in comparison to the Earth. So you can see that Jupiter's radius is 10 times greater than Earth approximately. And as you go down from the outer layers of Jupiter into the inner layers of Jupiter, the temperature goes up just like it does on Earth. The density goes up like it does on Earth, but also the pressure goes up, and the pressure goes up immensely. Remember that the Jovians do not have a solid surface. But as you sink down into the gaseous goo, the densities and the temperatures and the pressures rise so that the material becomes more solid-like over time. Think of sinking into a gigantic bowl of tapioca pudding. At first, there's some steam and some vapors, and then as you sink further and further down, it gets a little bit gooier and stickier and thicker. Eventually, you actually get to a layer where you compress the gaseous hydrogen into a liquid. This is extraordinary because hydrogen's probably hydrogen is the most volatile element in the periodic table, meaning volatile means I want to be a gas. I don't feel like being a liquid or a solid. It's impossible in a terrestrial laboratory to create the sort of pressures necessary to compress hydrogen into a liquid. So you might use liquid helium for some industrial applications, but you certainly don't use liquid hydrogen because it's difficult to make liquid hydrogen. Metallic hydrogen, forget about it. Only in the interiors of Jupiter can you create such extraordinary conditions. But it appears that after you get down to about a quarter of Jupiter's radius, the pressures become high enough to compress even hydrogen into a giant ball of metal. And that kind of gets me thinking, is it really fair to call Jupiter a gas giant? Because the majority of Jupiter's interior is a giant ball of metal. Let's take some notes on that. By the way, at some point we should talk about the test next week. At the urgings of some of your classmates, and out of a desire to show mercy on you poor sorry souls who've been taking astronomy remotely this semester, I believe I am going to offer you guys the option to forego the final by using your midterm grade as the same score as your final. So if you got a 50% on your midterm, you will then get a automatic 50% on your final. You can take it if you want to, or you can just use your midterm grade. How does the class feel about that? I know we had a quick discussion last week. David says thank you. David's not shedding any tears. David, I don't
Fantastic.
even know who you are. What's that, Jake?
Fantastic. Love the idea.
I like
Okay.
it.
Agreed.
That'll take some stress off everyone's life, right?
Yes.
I'm thinking of I've got to put all the questions in just in case somebody does want to take it. It'd be really nice. I need to know by the end of this week if you want to take the exam. Because if no one wants to take it, that means I don't have to do 8 hours or more of work. So that would be nice for me. If someone wants to take it, I'm happy to I have to put those questions in eventually. So I actually have to do that work no matter what. But I want to know if anyone is actually planning on taking it so I know what the hell is going on. Now, I know the whole class isn't here, but can anyone tell me, and I'm talking to all you trolls out there, well, I'm making an audio poll, and it starts now. Does anyone want to take the final exam?
No.
No.
Okay, all right. Everyone seems to be on the same damn page with this. Okay, you're welcome.
Bella.
Look, I like all this. Thanks. I can't even say this. Oh, I can't say who the hell is this? Could you clean it up? Actually, wait. I got a better idea. Instead of I banged Johnny's mom, thank you very much. I think where are you? I can rename this person. I'm gonna rename you here. I am immature. Okay, that's your name from now on. All right, so I am immature doesn't want to take the final exam either. Who can blame him? And I'm just assuming it's a him. I don't know why. That's a lucky guess there. Okay, so let's do an interior model of Jupiter. This is something that would be testable, okay? So this is the interior of Jupiter. Okay, we'll do a big wedge just like they did in the diagram. This is for your notes, okay? And at the top of the planet, we have a layer of gaseous hydrogen and helium, okay? Gaseous hydrogen and helium. And at some point, the pressure becomes high enough to compress it into a liquid hydrogen helium mix. So this is gas, hydrogen, and helium, okay? Eventually, the pressures will compress even this liquid hydrogen helium, let's call it a slurry. A slurry would be like a sort of slushy, watery ice bath, into a solid, and I want to stress the word metallic, hydrogen. Somewhere buried deep down in Jupiter would be that original planetesimal that swelled to large enough mass and size to capture some of what is no doubt primordial hydrogen and helium from the protosolar nebula. And that object would be a mixture of ices, rocks, and metals. And our calculations suggest it would be some kind of a super Earth. It would be something that was several times the mass of Earth and probably a little bit bigger than Earth in its radius, but not too much bigger. In the same way that Jupiter is kind of the largest sized Jovian planet that we believe can form, Earth is close to the largest sized terrestrial planet that you could form. If you actually calculate the thermal escape of hydrogen and helium from Earth's atmosphere, as we did in our previous lectures last week, you discover that Earth is just barely too small to capture hydrogen and helium. Had Earth formed with just a little bit more mass, maybe anywhere from 5 to 10 times as much, Earth probably would have been massive enough to capture hydrogen and helium, and our planet today would be another gas giant, what we call the so-called hot Jupiters, large gas giants that weirdly form close to the parent star. We have discovered a lot of hot Jupiters outside of our solar system, so we know it is possible for a terrestrial to form close to a parent star. It just so happened that it did not in our solar system. I want to just kind of dazzle you guys with some chemistry for a second and get you guys to consider why metallic hydrogen would probably be pretty weird. I want to show you
So-
guys. Oh yeah, Joel.
In that metallic hydrogen stage or layer,
Yes,
is there any helium in there?
yes, there will be helium. And if your question is that also solid? I am not 100. No, I suspect that would be. Well, I'm. You know, the only reason I paused to say yes is because helium behaves a little bit different than hydrogen in some ways. It's technically a boson, and that gives it some sort of strange properties when it's under pressure. I suppose it's possible. I just don't know the answer to it. Was that going to be your question, Joel?
I mean, maybe in a roundabout way. I was just curious because like there's hydrogen, helium in the gas and liquid, but then you didn't
Yeah.
add it or mention it in the solid.
I was sort of following the book there. There's a certain periodic table of the elements that I want, and I have it stored somewhere. Why the hell is it? Let me go to the Light and Telescopes lecture. Bear with me, class. 1021 definitely has it. I want this really pretty, colorful periodic table. Here it is, slide 16.
So do they like so do they like suspect that like in that solid core that like the helium would show up as like air pockets or something like that?
No. What happens if you throw a stone into a river, Joel? The stone sinks through the water down to the bottom. And the reason
Yeah.
why is because the density of the stone is 3 times greater than the density of water, correct?
Yeah.
Planets also go through a differentiation where the heaviest materials sink towards the center of the planet. Because rock, metal, and ice are all much denser than the hydrogen and the helium, they sink their way down towards the interior of the planet. So there won't be so much hydrogen and helium. There could be some small pockets, but
Okay.
if you smear out over the whole thing, very little hydrogen and helium should exist in the center by percentage of mass. Does that make sense?
Yeah.
Okay. I want you guys to notice something. If you ever took a chemistry class, let's say you've never taken a chemistry class, chemists like to make a big deal about the difference between what they call metals and non-metals. You'll remember, to an astronomer, anything that's not hydrogen or helium is sometimes cheekily called a metal. But metals are things which exist on the left side of this diagonal line. So you've got, in green, basic metals like aluminum. You've got transition metals like zinc and copper, nickel, cobalt, iron. Those are things that most average everyday Joes think of as metals. But then you've got these last 2 columns here, which are also different types of metals. There's an alkaline earth, and then there's alkali metals, of which hydrogen is a member, but so is helium, sodium, and potassium. One of the rules of the periodic table of elements is that elements which occupy the same column, they tend to share similar chemical properties. So all these guys are, for instance, noble gases. They don't really react with other elements. On the other hand, the alkali metals like hydrogen are extremely reactive because they have an outer valence electron which wants to interact with other elements. Now, I can't really show you a picture of solid hydrogen because you cannot create that in any Earth-based laboratory. But as an idea of what it might be like, let's consider the element sodium, which might share some small chemical association with metallic hydrogen. Here I need to share my screen with you guys again. Sodium at room temperatures is a very dangerous element to possess. Back in the day, when there were fewer regulations, they actually used to sometimes include little bits of sodium in chemistry sets that kids could have. You had to cover it in like a wax paper and you couldn't touch it with your hands, there's enough moisture in your fingertips to react to this stuff. It's actually quite dangerous. So it's hard to get your hands on a brick of sodium these days. This is what it looks like in a solid form. It's a sort of soft, porous, clay-like metal. And it has the remarkable property of being explosive when it comes in contact with water. So like I said, you can get a very nasty chemical burn. If you would even press your thumb against that clay brick there, you would probably either burn or set your thumb on fire. As a dramatic example, and this is just for fun to keep you guys awake in the morning, let's look at sodium in water. There's a video on YouTube of some crazy galoots throwing a brick of sodium in water. This is sort of like a classic recreational activity for crazy people to do. And there's one.
Explode? Yes, I've seen this.
This one's my favorite. Can you guys let me know if you can hear the sound here?
Who wants to throw it in?
Can you hear this sound?
I do.
I will. Here, give me the glove.
Yeah, you can.
I'm gonna just keep.
Yeah.
Oh!
You guys just like to see this, right?
Hold on. Hold on.
All right.
Wait.
We are recording.
Wait.
You want me to throw it real far?
Hold on. Wait.
Can I throw it real far or no?
This is so.
They've got maybe a 1 kilogram brick.
That's fine.
It was in my YouTube recommendations.
Oh yeah, this is just an awesome video. I love this one. They will not let me monetize my lecture after I show this to you, but I don't care. Watch this.
Okay.
Then it explodes.
Yeah.
That's some pretty fun stuff, right?
Oh,
No,
I saw
Guys.
2 videos of it.
say that again.
Yeah, I want to see it again.
Oh, you want to? All right. One more time for the people in the back. Okay. All right. Yeah. Well, fine.
I was not expecting it to explode.
Yeah, exactly. That's what's so cool. Here we go.
Catch it on fire,
Okay.
then it explodes.
Oh, that's a great video. Now, look, I'm asking you guys to consider that the entire interior of the planet Jupiter is basically a solid lump of metal that is an alkali metal, right? If you were to compare it, it wouldn't bear resemblance to, say, copper or nickel so much as it would resemble sodium or potassium. Now, students have asked me before, wait a minute, does that mean it's going to explode with the ice? No, probably not, although there could be some violent chemical reactions going on in there. It's hard to say, but it's not going to make Jupiter explode. Ultimately, remember that 98% of Jupiter's mass is in a hydrogen and helium form. Ice comprises 1%, right? Okay. Do you guys remember what the 2 conditions for a planetary magnetic field are? How do planets get a magnetic field?
Fast rotation.
Fast rotation is one. And
Atmosphere.
nope,
Metal core?
a hot, possibly liquid metal core. Noah, based on those conditions, would you assume that it's likely for Jupiter to have a magnetic field or not likely? Let's get rid of this here. Oh, sorry.
I'd say it probably doesn't have one.
Does Jupiter have a fast rotation?
Yeah,
It rotates twice as fast as Earth.
right.
Does Jupiter have a hot metal interior?
I don't think so.
What? What the shit have we
Oh,
been
is it-
talking
was it-
about?
Maybe.
Wait, hold on a second. Work with me here. Does Jupiter have a hot metal interior?
Yes.
Does Jupiter have a hot? It's 5,000 Kelvin before we even get halfway through its radius, and its entire.
All right, yeah, I'm gonna go with yes.
Yeah. Well, look, right, because that's what we were just talking about. The fact that it's compressed into a big metal ball, and that ball is like wicked, wicked hot, right? It's
Yeah.
as hot as some of the layers of the sun. So I would expect Jupiter, in fact, I'm just going to tell you the answer. Jupiter has a wicked powerful magnetic field. In fact, all of the Jovian planets have very potent magnetic fields because they all rotate very rapidly and they all have super hot metallic interiors. The Jovian magnetosphere, the magnetosphere of Jupiter, is probably the most powerful magnetosphere outside the suns in the solar system. And solar wind ions interact with it in complex ways, such that Jupiter actually has a sort of ring of charged particles surrounding its moons. This is kind of like the equivalent of Earth's Van Allen radiation belt. Well, we really didn't get to talk about that much. But Earth has a belt of charged particles surrounding it called the Van Allen radiation belt. And Jupiter has an immense donut, a torus. A torus is a fancy name for a donut of charged plasma that circulates around the Jovian environment. They call it the Io torus because its plasma strength is greatest near the moon Io. Because of this, there is a continuous current flowing back and forth in space. So there are free electrons flowing back between Jupiter and Io. And I think the strength of the current is around 1 million amps. 1 million amps. How many amps are in a typical house circuit breaker? You guys ever looked at your circuit breaker to see how many amps are flowing through there? Any electricians in the house?
15 or 20.
20 or 30. I think my dad's house is a 30 amp circuit breaker. There's 1 million amps, a current of electricity flowing back and forth between Jupiter and Io. I don't know. That sounds like you could power a damn star base with that. That's free electricity, right?
No thanks.
Well, free juice is free juice. You just got to learn how to tap into the lines. You know what I'm saying?
Yeah, but amperage kills you. Voltage doesn't.
Right. Okay. Well, you don't, put your face in it. You find a way to safely harness.
Yeah, but if it's just flowing back and forth, like.
So remember, I might have told you this in a previous lecture, but that means there's a total of 5 planets in the solar system that have powerful magnetospheres, powerful magnetic fields. All 4 Jovians have strong magnetic fields and Earth. And that's a kind of cute connection between Earth and the other planets. I'd like you guys to notice the difference in orientation between the spin axis and the magnetic field axis. As you may have heard, if you've done any exploration with compasses, geographical north is not the same as magnetic north. They're offset by about 12 degrees. And that's similar to the diversion between Jupiter's spin axis and magnetic field. Saturn has a perfect alignment between its magnetic field and its spin axis. But look at Uranus and Neptune. These planets have magnetic fields which are inclined by about 50 or 60 degrees to the spin axis of the planet. Now, I'm not sure anyone knows exactly why that is, although there are probably hypotheses. But remember that Earth has gone through periods of geomagnetic reversal over its history as well. It might be that the moment in time we're in today, we are just sort of capturing Uranus and Neptune going through some kind of a or I guess you can call it Urano-magnetic reversal or Neptunian magnetic reversal, whatever you want to call it. But those are things to think about. Okay, we're not going to take notes on that, but we will take notes on the next bit. Let's remind ourselves that actually, there's one other thing that I'd like to tell you guys about. One of the consequences of Jupiter and Saturn having super powerful magnetic fields is all 4 Jovian planets have massive auroras, just like the aurora borealis and the aurora australis on Earth. Here's a picture taken by John Clark with the Hubble Space Telescope's Wide Field Planetary Camera 2 of 2 massive aurora borealises happening at the north and south pole of Jupiter. Probably they have like a slightly different wavelength image superimposed of the visible image. This is probably infrared, but I'm not 100% sure. Look at the size of those auroral storms. That is a cosmic Pink Floyd light show that's probably 2 or 3 Earths in diameter. So that must be one hell of an aurora to witness. We've detected aurora on Jupiter. We've seen the aurora on Saturn. We've seen them on Neptune, and presumably Uranus has them, but I don't believe we have any images of the aurora on Uranus to date. One issue might be that it's flopped over on its side, which makes it harder to see both poles at the same time. Okay, other issues. Remember that during the Galileo mission, do I have a picture of this somewhere? I have a little cartoon. We dropped this small probe on a suicide mission into the cloud layers of Jupiter. Now, it did not make it so far down into Jupiter that it got to the liquid hydrogen, because the pressures were very quickly so great and the temperatures were so great that the spacecraft just succumbed to the pressure and temperatures and just crushed and disintegrated into probably a puddle of molecules. But we did sample some properties of the Jovian atmosphere on the way down. Now, first of all, Jupiter has kind of three different colored stripes on it, if you look at it here. And I want you guys to take a peek at these two images. The image on the left at the bottom shows you Jupiter at visible wavelengths. And you can see there are some sort of white clouds, some sort of yellow clouds, and some sort of red clouds. Notice that if you take an infrared image of Jupiter, like night vision goggles, wherever there are red clouds, you can see warmer temperatures. And remember, it gets warmer as you get deeper into the belly of Jupiter. And that suggests that while it looks like the clouds are all mixing at the same height, the red clouds actually lie deeper into the belly of Jupiter. Do you guys remember what the composition of the clouds were? White, yellow, and red? I listed them last time under hydrogen ices. Why don't you see if you can look that up?
White or water,
Yep.
the yellow or ammonium,
Yes.
and the blue or methane.
Right. What about the red?
And the red
There really aren't many
are
blue clouds in Jupiter.
ammonium hydrosulfide.
Right. So we'll take some notes on this, but let's take a look at what that probe discovered. First of all, you guys remember on Earth, we had different layers of our atmosphere, like the troposphere, the stratosphere, the thermosphere. How do you define a troposphere if there's no solid surface? You can see that what the scientists have done is they've decided that 0 kilometers in Jupiter's atmosphere will be right at the top of the clouds. And that's how they'll define the troposphere. Just like all of the rain cycle and the clouds on Earth lie within the troposphere, so all the clouds of Jupiter will lie within its troposphere. But they define positive altitudes as being above the cloud layer, and then below the cloud layer, the top of the ammonia clouds, you'll sink down into negative altitudes. Our probe made it from 200 kilometers above the cloud layer down to almost 200 kilometers below the cloud layer before the temperature went up to about 460 Kelvin. That's getting up to Venus's temperature, so the spacecraft is going to start to melt. And you'll notice the pressure is 20 times Earth's atmosphere, and that'll crush just about anything. Notice that one of the weird discoveries is that while Jupiter's atmosphere has an exosphere and a thermosphere, they were surprised to discover that Jupiter actually had a stratospheric bump in its temperature profile above the cloud layers. Now, students, what created the stratospheric bump in Earth's atmosphere? Do you remember? Why does Earth's atmosphere have a stratosphere? This would have been a test question. And based on the silent answers, I think it's a very good idea that you guys are not taking the exam. No? No one, this makes me want to give you an exam. No one can tell me where Earth's stratosphere comes from? Maybe you
I mean,
know.
I'm looking at the notes and I wrote down no convection, inversion layer, interactions between UV and ozone.
Oh, well, that's it then. You answered it.
Oh,
But you have to know what the answer is. So what's the answer? If someone asks you, why does Earth have a stratosphere? What's your answer?
because of the interaction between ozone and UV rays.
That's the right answer. Right. And we had a, it's coming back to me now. We had a chit chat about this. Let's do a share screen. Slide 25. Lightning bolts and other such mischievous processes create ozone in our stratosphere. Ozone is triatomic oxygen, O3. UV photons come down, they bust the O3 apart. The O3 molecules have high kinetic energies, and that heats up the surrounding gas. And then they come back together and reform O3, and so they absorb ultraviolet bullets from the sun. Do you think interactions between ozone and UV are the cause of Jupiter's stratospheric bump? Could that be the case? The stratospheric bump is considered a symbol of life on Earth because life created the oxygen. What about on Jupiter? Could its stratosphere be caused by interactions between ultraviolet and O3?
No,
Why not?
it's too hot.
No.
And there's no, well,
Its temperature is a balmy, 300 degrees Kelvin.
There's
I
no
thought I
life
was
to give off
asking a
oxygen.
wicked simple question. What?
There's no life to give off oxygen, so how could it
That-
interact with UV?
All right, that's point A, Jake. And point B is there's no oxygen to give off oxygen, right? What's the composition of the Jovian atmosphere?
Hydrogen, helium.
And maybe a little bit of hydrogen ices, right? Yeah. It's hydrogen and helium. There's no oxygen there. There must be some other chemical compound that's interacting with ultraviolet light to create the stratosphere. I'm not sure if we have a good idea of what that is or not. Notice that the yellow clouds, the ammonia clouds, sit on top of the ammonium hydrosulfide clouds. The ammonium hydrosulfide clouds sit on top of the water clouds. Why? Because these different hydrogen ices have different condensation points. We can see that ammonia is condensing somewhere around 170, 180 Kelvin. We can see the ammonium hydrosulfide condensing around 210 Kelvin. And we can see the water condensing at, take a guess, what do you think that temperature is right there? Kudos if you can have a...
273.
That's right, Joel. That's the condensation point of water. I just wanted to make sure you guys are with me. I'm going to ask you just random questions from time to time to see if your brains are working. I'm glad to know that it is. 273 Kelvin. Could you imagine what it would be like to take your flying saucer through the cloud layers of Jupiter? I mean, Earth has one cloud system, just water. And we can have some pretty nutty and wacky storms. Like that cool rainstorm we had this weekend, which was half rain and half hail and half snow. I guess a third rain, a third hail, and third snow. Anyone get caught out in that? That was a mess, right?
Yes.
Now think about
sucked.
that. It did suck, actually. And think about the suckiness of that storm. That's one cloud layer. Having had that experience recently, could you imagine going through a triple storm system on Jupiter where flakes of ammonia snow are raining down up on top of ammonium hydrosulfide rain and then hail from water clouds? You could have triple the storms, triple the lightning bolts, triple the cyclones. In fact, there are, if you don't remember, some pretty nutty ass storm systems on Jupiter. One of the most famous, of course, is the Great Red Spot. It's a hurricane system that's persisted since we've been observing Jupiter for about 300 years now. This thing has been there. And the hurricane system the Great Red Spot, is like 2 to 3 Earths in diameter. What causes hurricanes to dissipate on Earth? What usually breaks up a hurricane?
Land.
Land.
So can you think of a reason why this storm system might have persisted for so long?
Well, there's no solid land.
Yeah, that's interesting, right, Jake? Without the solid continents and stuff, these things can just go whipping around forever. Now, Jupiter has, these things are smaller. When I say smaller, I mean, that's probably the size of Earth right there. It has some nasty storms, but the Great Red Spot is just weird in a couple of different levels. The Great Red Spot is actually a high pressure storm system. Usually we get hurricanes forming when there's low barometric pressure on Earth. That tends to create foul weather. There's something different about the Great Red Spot. It actually sits high above the clouds. That also probably contributes to the fact that it hasn't dissipated. We've wondered if perhaps this storm system will dissipate someday. After all, you guys might know about the Great Red Spot, but I'm guessing you've never heard of Neptune's Great Dark Spot. This is a picture from the Voyager 2 mission where we got up close and personal, and we actually saw a similar kind of storm system in the cloud layers of Neptune. The Great Dark Spot was there in the 80s when we went past it, but all subsequent images from the Hubble Space Telescope have seemed to suggest that the Great Dark Spot, as it's called, has disappeared. Now, we were wondering if one day the Great Red Spot might also disappear, causing Jupiter to lose one of its iconic features. But what happened instead was actually a lot more wacky. I want to introduce you guys to, wait for it, Great Red Spot Jr. Instead of the Great Red Spot disappearing, in recent years, a new Great Red Spot has made an appearance. Let's see if we can find a nice picture of Great Red Spot Jr. somewhere. I guess maybe this is one of the better ones I'm going to find. So it might be that Jupiter's Great Red Spot, it's possible to have multiple of them, I suppose. It's some kind of a cool atmospheric phenomenon that takes place in the Jovian system.
Is that a third one that's forming?
It did look like that in that image, didn't it?
Yeah.
Let's just take some notes on this. Those are the kinds of things I'd like you to have in your memory books from our class. Let's take a quick note on the cloud layers of Jupiter. So I'm just going to do this whole thing in black and white in the interest of time. So if I had colors, it would have been nicer. So the top layer clouds, these are yellow, and these are caused by ammonium cloud layers. And, you know, like maybe 170 Kelvin is the temperature at which they're condensing. The middle layers are red. They are ammonium hydrosulfide. That's the like stink bomb chemical that I told you about last time. And they were condensing around maybe 220 Kelvin. Those numbers are approximate. And then the bottom layer clouds are white. And they are caused by H2O, water, ice, whatever you want to call it. And those are condensing around 273 Kelvin. Remember, they're under some kind of an atmospheric pressure, so they'll have a similar condensation point to the condensation of water on Earth. And that's all in its troposphere. So if you had to say what color Jupiter was, it's kind of three colors. It's yellow, red, and white stripes. What if we were to talk about Saturn? Can you guys think about what color Saturn is? maybe I should just show you a photo from the Cassini mission.
Isn't it like yellowish brown?
Yeah, indeed, Joel.
Like a mustard color.
I want to show you the interior layers of the other planets, and I want to show you their cloud layers too. So first I'll do this, slide 23, and then I'll show you slide 42. So 23 and 42. You'll notice that while all four Jovians have the same composition by mass, Jupiter and Saturn have a similar differentiated layer where they both have clouds, gaseous hydrogen, a sort of liquid hydrogen layer, and we believe a metallic layer. Saturn is 1/10 the mass of Jupiter, and Neptune and Uranus are both about 1/100th, are both about 1/100th the mass of Jupiter. So Saturn is still massive enough to compress hydrogen into a liquid and a metal, but we believe that Uranus and Neptune actually have a lot more ices in their interior than, well, a little more ices than Saturn and Jupiter. We do not believe at 1/100th Jupiter's mass they are heavy enough to compress hydrogen into a metallic layer. For this reason, we sometimes differentiate them and call them ice giants. And I mentioned that last time. Somewhere below the gaseous hydrogen is a slurry of metals and ammonia and water and methane. The reason why they have more ices is as you go further out into the solar system, there are not only frost lines for water, but ammonia has a frost line and methane has a frost line. And you're getting to cooler temperatures where there's even more ice making up the mixture of the material. If you look at the cloud layers, slide 42, what do we see happening here? So my point that I'm trying to get at is all four Jovians have a different color scheme and a different color profile, yet they're all comprised of the same basic elements. They all have the same compounds in their atmosphere. Notice that, for instance, Saturn has ammonia, ammonium hydrosulfide, and water clouds, just like Jupiter does. Let's look at a picture of Saturn. We'll come back to slide 42 in a second. Let's look at a Cassini image. Sorry. How would you describe Saturn's atmospheric clouds?
Yellow.
Kind of yellow, Andrew. You can see that there's almost some stripes like on Jupiter, but they're a bit washed out. Can anyone answer me this question? Why does Saturn's color and atmosphere look different when it's comprised of the same compounds as Jupiter's? What's different about these guys than these guys?
The altitude is lower on Saturn.
Good, Jake. That's exactly what I wanted to hear. Why is the altitude of the cloud layers lower? Can you follow up with that? Why would the clouds be forming further down inside of Saturn?
Does it have to do with the atmospheric pressure?
A little bit, but more the temperature. Jupiter is 5 astronomical units from the sun. Saturn is twice that distance, 10 AU from the sun. So work with me here. What's going on?
They need a certain temperature to condense into clouds, and that temperature is only available closer to the first layer of Saturn,
Beautiful. You have to go deeper in before it's warm enough for them to condense, right, Jake?
Yeah.
That's correct. So, okay, so they're condensing deeper within the interior of Saturn. So why did Saturn look all kind of washed out in yellow then? This might be a little harder to answer, but give it a whack. Everything you've said so far is correct. Well,
So you have to get further into the troposphere
yeah,
to
it's
to
about the
get
depth.
to get the same or same relative pressure
Yeah,
as you
like
would
this is
on
height.
Jupiter.
All the clouds of Jupiter are separated by a few tens of kilometers. So you can see those three stripes. But with Saturn, you're actually looking into a much deeper layer of ammonia haze. So this is why Saturn tends to look yellow and hazy. Where was that picture again? You're looking deeper into Saturn before you can see the stripes. So you're forced to look through an ammonia haze that's washing out the stripes and making it appear a kind of washed out yellow color. Now, famously, when we go out to Uranus, Uranus has a green color. And the reason why is Uranus is 20 AU from the sun. And now you're getting to layers, sorry, I'm bopping around here. Now you're getting to layers where it's cold enough for methane to start condensing. You really don't see much blue in Jupiter or Saturn's atmosphere because it doesn't quite get cold enough for methane to condense. It's below 100 Kelvin, right? But once you start condensing methane, methane has blue clouds, ammonia has yellow clouds, and as you all know, yellow plus blue
is green.
That's right. So then why is Neptune blue? Anyone who's been following me should be able to take a stab at why Neptune is blue when Uranus is green.
Is it a mix or wait? So,
So
it's because of
here,
water freezing up because it's an ice giant, right?
no, it's not water. So remember, Jupiter is 5 AU from the sun. Saturn is 10 AU from the sun. Its color is yellow, right? Uranus is 20 AU from the sun. Its color is green. Neptune is 30 AU from the sun. Its color is blue. I'm trying to get you guys to answer why. They all have the same composition, but they look totally different.
Well, the size of the
False.
planet,
The size of Neptune and the size of Uranus are essentially equal. They have the same mass and they have the same radius.
well, no, like the size compared to Saturn and Jupiter, and so the atmosphere and the pressure is smaller, and the distance.
Sorry,
from the sun,
you're a little all over the place, Joel. Size has
Yeah.
got not much to do with it.
Oh, okay.
I think it's like the same deal as the last one, where like you're
Yes.
just looking deeper into a layer of methane.
That's right, because it's colder. You're farther from the sun, it's even colder. Just like on Saturn, where it was twice as far away, the clouds had to form deeper in. On Uranus, you're actually getting a little mixture of ammonia and methane to give the green color. But on Neptune, the ammonia clouds must be deeper in, which gives it a lot more blue methane clouds. It's just temperature. What fundamental planetary property then determines the color of our Jovian planet? If you just had to sum it up into a big picture idea, what is the fundamental planetary property that determines what color my Jovian is?
The level of ammonia.
Nope. They all have the same level of ammonia. Percentage-wise, it's the same. This is my point. You've got the same freaking bag of Bisquick. You've got the same ingredients, but something's changing that makes their appearance so wildly different. And it's not their composition. They're all made of the same shit. Jake?
It's temperature.
It's temperature, but what's the fundamental planetary property associated with that? What are your 3 fundamental planetary properties? Go back in your notes, find them and regurgitate them. That's how we learn.
Size, distance from the sun, and rotation rate.
So pick one that best describes what the heck I'm talking about, Jake.
Distance from the sun.
That's right. Isn't that funny? It's your distance from the sun and therefore the temperature that's really affecting why Saturn looks like this, why Uranus looks like that, why Neptune looks like that. You're just seeing different condensation points of different cloud layers. And this is why, of course, Jupiter looks wild with like these stripes. If you moved Neptune to Jupiter's distance, I suspect it would over time start to look more like Jupiter. I think you'd see these same rotating cloud layers in these same colored bands. That's an interesting thought. It's fundamental planetary properties that are affecting how these things look. How am I doing on time? Oh my God, it's 12:58. Where does a day go? I hope you've all learned something. I'm hoping we'll be able to do next class. We're going to do one of my favorite topics. So I guess we should talk about this. Next class is the last class, right? And if you're not taking the exam, the next class is the last time I ever see you, correct? So please show up and give me your best rah, rah, rah. Okay, I'll try to show up too.
Unless you do unless we can do the telescope to see Jupiter and Saturn.
Oh yeah, if I set that up on the 21st, if it's not too cold and it's not too COVID, I mean, I don't know if you guys have been paying attention, but the numbers are really bad right now. Have you noticed that? Like, it's worse. Remember when we were all freaking out playing jigsaw puzzles in like March? It's like 4 times as bad as that right now.
It got bad as soon as my parents got COVID.
Really?
Like,
Are
I'm
they
on
okay?
quarantine right now. Oh
You're
yeah,
on-
they're fine. Yeah, I've been on quarantine for like a month now
Oh my
because my
gosh.
dad got it, and then like a few weeks after my mom got it. So, and then as soon as they got it, the world like went to shit, and I was like, "Oop, good thing I'm inside."
Oh my God, I know. I feel like people I know are starting to get it or have people they were in contact with. I can't believe I haven't gotten it. I'm surprised at this point, or maybe I'm an asymptomatic super spreader. I don't know. But it's kind of coming for all of us. So we got to be real. It's especially scary because the hospitals are kind of full up right now, right?
Yeah, my mom's a nurse. She said that it got really bad at her hospital very quickly.
Oh,
That's because no one's really giving a crap anymore. They're like, oh, it's just a daily thing now. So, because I go to the stores as little as possible, but people are not even wearing their masks. They're like arguing in the store saying, I'm just going to do a quick run in. I don't need no mask. Like, they're not really giving a crap or saying.
Yeah, that's really socially irresponsible. I don't like wearing a mask more than anyone else, but I do it because we have to do whatever we can to save our fellow country people, right? Like we and our fellow citizens. Like it's social responsibility, and it is. You know what? It's hard too. Is it wears down on us? Like we're probably all tired of sitting inside of our apartments playing checkers and stuff, and we want to go back to normal, and we just can't do that yet. So, anyways, I only mentioned that, Joel, because I want to take you guys to the telescope so bad, but with the numbers so stupid high, it might be really, really socially irresponsible for me to do so. It's a terrible. As an educator, I want to one of my favorite parts about this class is when I actually get to take you guys to the telescope and you get to do something real. And it's real sad that that's not happening this semester. So I don't know what to do about it. I feel like it could be real risky to do something like that, Joel, but I'm thinking about it.
Well, the interesting thing with the COVID stuff is, so the Baltimore Ravens, they had 20 people test positive, and they found 4 different strains of COVID.
Oh no!
With those 20 people.
Oh no!
So I mean, that's
like, really scary.
Well, they had said during the summer that it's good, that it's going to morph into crazy stuff, and so I mean, it's just
I'm
But-
not
but you-
surprised.
but you
That's what
can't-
happens when it gets like passed from person to person.
Right. Right. And
It's gonna
that's-
happen at some point.
That's scary because I don't know if the vaccines are going to protect you from all 4 strains, which is
Well,
pretty
because
long.
once you get COVID, your body's going to build up the antibodies, and then as the virus goes from person to person, it's going to mutate, and then
Right.
the
And
antibodies aren't going to affect it. And
I read a story this week about someone, the second time reported time of a person getting reinfected with COVID. So perhaps that some of the mutations are wiggling around enough where the antibodies don't protect you anymore. That's the really
I
terrifying
think
thing.
they
This-
said it's good up to 3 months and then you can get it again.
Oh my God.
Well,
All
there
right,
was
look.
a football player during the summer that got it twice within like.
Oh, I
a
can't see the
month.
board, Brendan.
I'm sorry,
Need
Andrew.
one.
Okay, look, well, obviously this is a big topic and I'm just in the dark as you guys are really. So I hope it gets better. In any case, here's my point. My point is it could be that next class is the last time I see you. So today we're going to try to do a lab. I'm a little worried that I'm not going to be able to get this splash thing up and running, but I'm going to try during our little tea break here. I'll see what I can do about today's lab. On Wednesday, let's do one final homework on the Jovian worlds. That in place of an exam, that's kind of like our last, we're doing a job together, you know, and we'll do the homework as normal. And then after that, make sure your homeworks and your labs are in, and I'll double your midterm exam grade and you should be good, okay? I haven't graded this past week's work yet. I was a little bit of I was naughty yesterday, so please forgive me. But I will get to it. I'll try to do it today. Okay, I'm gonna take a tea break. You guys take a tea break. David, the idea is that we're gonna print the massive Jupiter lab, although I was telling the students beforehand that I was having some trouble with it. It's lab number 11. It requires me to do a simulation on the computer. So please print massive Jupiter and we're gonna see what we can do. I may have some previous data we can use, but that'd be kind of lame. Just sit tight, guys. I'm gonna take a 15, 20-minute break, okay? I'll be back. Hello, students, we're back, and somehow, by the grace of God, I've managed to actually get the lab running today. I was a bit touch and go there for a second. So hopefully you've got your massive Jupiter packet. Let me activate my Wi-Fi because we're going to need to use the phone at some point. And we're also going to take observations of the planet. Let's see here. I'll explain our goal here in just a moment. Let me just turn on my bloody Wi-Fi. Okay. The goal of today's lab is to estimate the mass of Jupiter by tracking the rotation of the moons around the planet. So what's going to happen is, let me just go to my whiteboard here for a second. We're going to see Jupiter as a disk, okay? So here's Jupe. And we're going to see the 4 Galilean moons orbiting back in front of it each day. Now, the 4 Galilean moons, which we'll learn about next time, are Io, Europa, Ganymede, and Callisto. For ease of access, we'll probably just focus on Io. So the moon will go kind of start at some position, it'll orbit all the way out to its greatest elongation, and then it will turn around and come back the other way, and we'll basically track it as it goes back and forth in front of Jupiter. We'll see the moon orbiting in the plane of the disk. Remember that there is a formula called Newton's version of Kepler's third law. It tells us that the mass of Jupiter plus the mass of the moon, which is probably insignificant, can be calculated by 4 times pi squared times a cubed. Remember that a is the semi-major axis of orbit. That's basically the same as the radius of orbit. From here out to here, that distance there is a. It's the radius of orbit. And then, of course, it's divided by big G over p squared. That's the version of Newton's Kepler's third law that we are accustomed to using. Here, the mass of the moon will be insignificant. So if we can just measure its orbital period and its radius of orbit, we should be able to calculate the mass. We're going to use a slightly different version in today's class. The version that we're going to use is that the total mass, the mass of Jupiter, is just simply a cubed divided by p squared. And we can use this cheesy version of the formula if we convert our a to astronomical units, if we convert our period to years, then our mass will come out in solar mass units. It's just a cheaper version of this formula that doesn't use MKS. That'll cut down on our unit conversions. Okay, let's go ahead and let's find our data sheet for EO, which is the first thing we want. I also need my tape so that I can hold my phone while I take the observations. And just give me a second here. All right, we're only going to have to turn in a couple of pages. So let me share my screen with you. Let me share my phone with you and we'll see what's going on there. Share screen, iPhone, share, screen mirroring. Okay. Everything seems to be working in order here. You guys can see my phone, correct?
Yeah.
All right. So I don't think we're going to need to turn in this page or this page. We might need some data from it, or this page, or this page. That's a sample. We will need this page. This is our data table page, and that's probably the first one we're going to need. So let's get out a pencil here. I had a nice black pencil earlier, but okay, this will work. So please put your nomen at the top. This is lab number 11. This will be our final lab. And as always, you are astronomy 1010. Your section is 01, 002, or 003. Okay, we are going to choose for our dates. Let's see if we can do the starting date today. So I'm going to have to go back and forth between, before I have you write all this stuff down, we're going to be filling out the date. We're going to be filling out the time window. We're not going to measure the distance to the moon in millimeters. This is not from a photograph. We're going to measure it using our computer simulation, where we get the distance to the moon from Jupiter in a unit called Jovian diameters, or Jupiter diameters. So basically the diameter of Jupiter is 1 Jupiter diameter, and we can convert that to astronomical units later. They give us the conversion in here. Let's see if we can find it right now. I think it's 454 times 10 to the minus 5. There it is. So we can go from Jupiter diameters to AUs using the conversion factor 9.545 times 10 to the minus 4 AU per Jovian diameter. Let's write that number down before we forget it. Let's write it up here. So that's 1 Jupiter diameter equals 9.545 times 10 to the negative 4th AUs. Kind of a weird conversion, but all right, we'll take it. Have you guys got that?
Yeah, I get it.
Okay. I'm hoping we can set this up so that the date starts at today. And I believe since we're going to do the moon EO, the other sheet that we're going to need is the data sheet for EO. They have data sheets for each of the 4 Galilean moons. If we were doing this in a lab together, I'd probably assign a moon to each team. But since we kind of have to do it together, we're all going to choose the moon Io. That's the closest, or Io. Io is the closest moon to Jupiter. And Io, notice it has us doing observations. This is 4 hours. So we kind of want to take an observation every 2 hours. If we make an observation every 2 hours, then our data points will graph onto the grid quite nicely. So you're going to see me set that up. So I'm hoping, let's go back to our data sheet for a second. We have this and we have this. And the only other sheet we're going to need is that last one with the data analysis over here. So I'll put those to the side. And I'm going to grab this puppy again. And we'll worry about the dates in a second, but we want our observation interval to go 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. And when we go back to a new day, instead of 24 hours, it will return to 0 hours. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and back to 0. Let's just fill this whole page in now so we don't have to take those datas each time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 0, 2, 4, 6, 8, 10. That's about all we're going to need here. We probably won't even need this whole page. So you guys see how I did that?
My paper doesn't go long enough.
Well, then you'll have to go on to page 2, I guess, right?
Yep.
Oops. We might not need to fill up this whole page, Andrew. Before we do the date, let's make sure that I can get this thing actually working properly here. I'm going to stop share, which is always dangerous. Let's go to my Revolutions of the Moons of Jupiter lab. Okay, I've got to set this thing up right. So data preferences. File, run. So it's going to start 2020-12-7. So we'll hit OK. And here we can see, if we zoom in, you guys can you see Jupiter and the 4 moons there? Yep, little simulation. Let's go to our timing data. We want our observation step to be every 2 hours. Data interval, 2 hours. I think that'll get us right. And notice that our universal time here, we're going to use this for our clock. That's our number of hours. And the date is December 7th, 2020. So that's today's date. So what we're going to do is, let's see if I can share to my phone again. Pray that this all works nicely. Oh, the gods are with us today. Okay. So the first date is 12/7. Oops, sorry, 2020. And so my lamp here is a little bit intense. So that's going to go all the way up to the next 0. We don't have to write it 100 times. This will be 12/8/2020. And that will go up to 12/9/2020. And that will go to 12/10. So can you guys do that as well? So we kind of filled in that first 2 columns already in advance of our data collection. I'm just going to give you guys a second to work on that, because I know it's helpful just to take a moment to write it down. I'll pause the video for a second. Can I pause the video from up here? Pause. Okay. So does it say recording in your upper left corner, Jake? Joel, does it say recording? Okay.
Yes.
All right, I got that.
So I just pause it for a sec to give the class time to catch up to this stuff. I figure if you're in the night class, you can hit pause on the recording and make sure you have all of this, okay? Okay, so our goal is to take measurements of the planet in terms of Jovian diameters each day. There are going to be some cloudy skies from time to time, and I'll tell you how to deal with that at the appropriate time. Let me stop sharing the phone again. I'm going to show you guys the simulation. Share screen. This requires me going back and forth between phone mode and computer mode. Hopefully that'll be smooth. Okay, notice if I click at random positions, it tells me an X and a Y coordinate, and it tells me on the X axis how many Jupiter diameters I am away. We have to first find our moon by clicking on it. That's actually Callisto. That's Io right there. And according to this, Io is 2.78 Jovian diameters west of the planet. So that's going to be our first recording, 2.78 west. So let me go back to phone mode. Hopefully this will keep working flawlessly here. So I don't want to do this each time. So I want to trust that you guys can get this down. So it's 2.78, and we have to record east or west. Do you guys see that?
Yep.
Okay, now I have something to ask of the class. Do you see how I recorded this? From now on, I don't want to keep switching back and forth between phone mode and simulation mode because it'll take lots of time. I want to be able to call out the numbers and have you record them as I say them, keeping track of east versus west. Do you think you guys can handle that?
Yes.
All right, nice. If you get any questions along the way, let me know. Try not to skip a day or do anything stupid, and I'll try not to do that too. It's easy to screw this up. Okay, now that we have our value, 2.78 west, we're going to see the moons move once we hit next. There's no going back, just like in real life. Let's zoom out to 200 level, and there was our moon. Let's keep track of it. Next. Looks like Eos moved to about there. 2.38 west is the next recording. .38 west. Now listen, if you're following along at home, notice that it says here, universal time is 2 hours. Let's all make sure that this clock here corresponds to our time slot in hours. That's how we know we're not screwing up, okay? Does everyone have 2.3 west? I'm ready to move on if you are.
Yep.
Let's see if we can do this pretty rapidly. Okay, we got to figure out which one is EO. 1.73 west. I'm going to go next. 1.73 west, okay? Next, I bet that's EO. 1.03 west. I'm going to go next. Okay, notice that the moon has sneakily gone behind Jupiter, or it could be in front, but I don't see it. Sometimes you can get lucky and just click on it. When the moon goes behind Jupiter, here's how we're going to record the data. We know that it's 0.5 Jupiter diameters west to 0.5 Jupiter diameters east. And Io is hiding somewhere behind there. Those are different moons. That's Callisto and Ganymede. So Io is back there somewhere, but we don't know where. So the way that we're going to record this is share screen iPhone. We're going to record this next value as less than 0.5 Jupiter diameters. That's the less than symbol. We know it's less than 0.5 east or west, but we don't know which one it is. I'll show you how to plot that later. When we plot less than 0.5 Jupiter diameters, it means it could be anywhere from 0.5 east to 0.5 west, but it's unknown. Does that make sense?
Yep.
This will tell us later that it went behind the moon. Okay. By the way, every time it goes behind Jupiter, we'll record it like this. If we see any cloudy skies during the simulation, we're going to record CS, meaning that day had cloudy skies. Back to the game. Okay, so let's zoom out again in case EO pops out and hit next. I still don't see it. So let's just make sure that's not EO. Yeah. So it's less, once again, record again less than 0.5, just like you did last time. That's 10 hours. Now next should pop it out from behind Jupiter. Okay, here we go. There's EO. 1.51 east. I'm going to move on next. 2.20 east. Next. 2.69 east. Next. 2.90 east. This is just how it looks through a telescope, by the way. Next. Ooh. 2.94 east. Notice it's kind of getting to the edge of its orbit there. That must be close to this radius of orbit. Oh, can you guys see that? That dark shadow is a transit. You can see the shadow of one of the moons on Jupiter. I've actually seen that through my telescope before. That's just how it looks. You can see the shadow. In fact, I could show you guys a legendary picture just to, you know, juice up your caboose here. There's a legendary photograph from the Galileo mission of an up-close version. And this is a real photograph here. Isn't that cool? Here's the moon, and there's its shadow on Jupiter. How cool is that, huh? Okay. Any case, that's not EO causing that. I don't think so anyways. EO is 2.94 east. You guys got that?
Yep.
Yep.
Okay, let's move on to 22 hours. 2.66 east. Next, 2.18 east. Next, 1.50 east. Next, 0.71 east. Next. Okay, now EO is in front of Jupiter, so we can actually get a recording of its position. And that's probably the shadow of EO there. So we got 0.16 west. When EO is in front of Jupiter, you actually stand a chance at seeing it. Next, I guess there's no cloudy skies. That's kind of lame, but whatever. Actually, it's kind of great. 1.03 west. It would have been nice to show you how we deal with the cloudy skies, but I guess that's not going to happen. I thought they were set up by default. 1.79 west. And that's 10 hours. Yep. Next. 2.39 west. Next. 2.81 west. Next. 2.95 west. Am I going too fast for you guys?
2 point.
I'm doing
All right. Yeah, I'm trying to pace myself. It's hard to know what's good for you guys on the other end. Sharp pencils, sharp lines.
That's for 16 hours on 12/8.
Yep, 16 hours, 2.95 west. Let's hit next.
All right.
2.95 seems to be as far as it goes. 2.84 west. Here it's coming back in again. What just happened? Oh, the others are farther out. Let's see if I can zoom out. Yeah. $2.51 west is 20 hours. $1.39 west. Well, I'm sorry, 1.93 west. Apologies. 1.93 west for 22 hours. 1.21 west. Less than 0.5 Jupiter diameters. Less than 0.5 Jupiter diameters. Oh, how about that? Cloudy skies. This is like real life observations. Sometimes you have gaps in your data. It's important that you record this as CS. Do you see how I did that, guys? I don't know if you can see. So you record it as CS. You don't want to skip the data because the moon was moving that day, but we didn't get to see it. This is a gap in the data, and we're going to do something called interpolation. Have you guys heard of extrapolation, where you go beyond the data? Interpolation is when you go in between the data to fill in the gaps using guesstimations. Cloudy skies are the bane of real astronomers' work. Some of my friends have gotten time on serious telescopes like Kitt Peak in Arizona and flown out to Arizona only to have the clouds come up and the sky gets snowy and then lose their time at this world-class telescope. And no, you don't get a makeup day. This isn't kindergarten. You lose your observations, and that sucks. Okay, let's hit the sky, hit the clouds again here. So that was cloudy skies was 6 hours. 8 hours is also cloudy skies, right? Another CS. Oh my God, 10 hours is cloudy skies too. They're really going nuts in the cloudy skies. That's 3 cloudies in a row. And finally, we're back to biz. Let's see if we can figure out which one EO is. Wow, it's jumped all the way to 2.89 east. That's 12 hours. 14 hours, 2.95 east. That seems to be about as far out as it goes. $2.78 east. $2.34 east. $1.69 east. $0.91 east. $0.06 east. $0.81 west. $1.60 west. $2.26 west. $2.73 west. And one more. 2.94 west. Okay, that ought to cover us for the data collection portion. Someone's chatting me. Let's see what the chats are saying. Okay, Ava, sure. Ava wants to see all the numbers again. I don't know if I was going too fast or Ava was just trying to wait for them all to get done. But no matter what. Oh, okay. All right, so several of you are in the same boat. Let's see if I can share phone again. Share screen, this time to iPhone. Okay. Let me go to my display. I need to turn off auto lock. Wow, I can't believe how. Joel, remember the days when my phone wouldn't work? When they must have updated the patch or something. Okay, so let me get rid of this glare here. This is the first part of the data. And now we'll scroll down to the second part of the data. Let's see if you guys want to try to, can you see all of it at once? That might be kind of hard to read.
So it looks like it's about 42 hours for Io to orbit.
Very good, Joel.
Jupiter.
We're going to plot it out so you can see what it looks like as a plot, but how did you get that? Just by counting until you got back to the same place?
Yeah, I mean, December 8th, 1800 hours.
Joel, you've got a scientific mind. That's exactly what a scientist would be doing, would be looking at the data to see if they could draw conclusions from it. So I like your style, sir. You have good science style. One of the reasons I like this lab, even though it's a simulation, is it definitely taught me a lot about how one could go from telescopic observations to actually determining a physical property of a planet. And after all, that's the journey that science is about. You start by looking at things, and then you try to deduce something that an ordinary person couldn't see by analyzing the data. That's our next step. Ava, have you got all this down enough? Can I move on to the next part, or do you need a minute? Does anyone need a minute here? Ava's chatting me. Speech would be nice too. Wait, what does yes mean? Does yes mean you're set, or yes, you need another minute? Done. Okay. Okay. Cam, you too, right? Okay, Cam's chatting yes. All right, fine. Okay, so with our data table to the side, let's get the graph. And this isn't going to be the worst graph you've ever had to do because I set it up to make it easy for us. I set it up so that our observation interval was in 2-hour increments, which is exactly what these increments are, meaning each data point will fall on one of the lines. This will be 0, and then this will be 2, 4, 6, 8, 10, 12. Notice that these increments go 0, 0.51, 1.5, 2, 2.5. So our first data point is 0 and 2.78. So this is 0, 1, 2. If that's 2.5, 2.78 is about halfway up on that line. It's close to 2.75. So put your first data point loud and proud right there. The next one is 2.38. So at 2 hours is 2.5. 2.38 should be almost, but not quite up to 2.5.
Can you tell me the name of this graph?
This graph is the orbital velocity curve for Io. It's actually the orbital position curve. We're plotting distance from Jupiter. Oh, I guess we have chosen west to be positive and east to be negative. Could you please make note of that? This is not an orbital velocity curve. It's an orbital position curve. Dummies. Okay. Okay, so that was 2.38. The next is 1.73 west. 1.5, 1.73 is about 3/4 of the way, or 2/4, halfway up. Okay, the next one is 1.03. So this is 1, and just above 1 is where we ought to be. That's 1.03. Now at 8 hours, we have, okay, we know that at 8 hours and at 10 hours, it's less than half a Jupiter diameter. So for this data point, we know the data point falls somewhere within this box. So make a box from negative to positive 0.5. Same thing with the next observation. The next observation, and this is where we're going to interpolate. We know that our line must pass somewhere through these two boxes, but we don't actually know exactly where the moon is in those dates. That's how I'm choosing to do this. You can follow my lead if you like. Now we'll go to 12 hours. It popped back out at 12 hours at 1.51 east. So that's basically at 1.5 negative. There it is. Okay. The next one is 2.20 east. 2.5, 2.20 should be about there. Then we have 2.69 east. 2.5, -3, 2.69 should be, I don't know, somewhere about there. Next, we have 2.90. That's almost at 3. And that's at 1800 hours. 2.94 is even closer to 3. 2.66 backs up a bit. 2.18 should be close to -2.2. Negative 1.5 is right there. That's an easy one. Negative 0.71, that's 0.5. We'll call that negative 0.71. Negative 0.16. So that's negative 0.5. Negative 0.2 is like right there. Whew. Did I do something funky here? Look at this little goof up. That's negative 0.16. Oh, look what I did. Look at the dingus that I am. Negative 0.71 should be below -1. This is the -1, sorry. This is the -1 line. And I could tell because my data didn't look smooth. Can you guys change that dot to just below that line? Did you guys see that mistake I just made there? No one caught me. All right. And I could see something was unsmooth in the data, so I was concerned. Okay, this is at 6 hours on the 8th. Now we have 1.03 west. So basically, wow. All the way up to here, huh? Okay, fine. 1.79 is 1.8. That's almost +2. 12 is 2.39. That's 2, 2.5. That's 2.39, somewhere around there. 2.81. 2.81 is getting close to +3. 2.95 is very close to +3. 2.84 is back.
Wait. Hold on. What was it again?
2.95 is 16. 18 is 2.84. That was my imagination of 2.84. 20th is 2.51. That's basically like 2.5. We'll just put it right there. 22nd is 1.93. That's below a little bit, not too much. Wait, sorry.
When does it start to go down? I got really lost.
Well, I'm just plotting the data as I see them. And you can do it too. You don't need to follow me, but I'm just showing you where I would put the points, right? I was thinking plotting these points would be a skill you guys would have here.
All right, I got it.
Because you can't see the x-axis from my phone, let's just do a little member in here. This is +1, and that's +2, and that's +3, okay? So this is 0.51, 1.52, 2.53, okay? So now we're moving back to 0 hours. What was this? This was 1.93, and 1.21 is maybe somewhere about there. Okay, the next two are less than 0.5 Jovian diameters. So once again, we're going to swirl out some boxes where it goes behind the moon. Or sorry, it goes behind the planet Jupiter for 2 observation periods. So I'm going from somewhere, but it could be anywhere from -0.5 to +0.5. And then on the 6th, it reemerges. Oh, shoot. And now we've got cloudy skies. So we have to leave it blank for cloudy skies. And we don't know where the data point is. So we have a cloudy sky at 6, a cloudy sky at 8, a cloudy sky at 10. Those are missing gaps in the data. And then at 12, it's 2.89 east. So that's -1. That's -2. 2.89 is almost to -3. Then it goes to 2.95, which is basically right at 3. Then it goes back to 2.78. Then 2.34. Then 1.69. 1.5, that's 1.69. Then 0.91 is just, 0.91 is just where the hours are. 0.06 at 0 at 24 is basically 6 east. It's basically almost on the line. And I think we can stop there. Notice, let me see if I can turn my phone sideways here without this fucking thing. Okay. Wait, hold on. There we go. This is what things be looking like. That's what you should have. Do you guys see that? Okay. Now we're going to do a kind of Pee Wee Herman connect the dots, la, 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 but try to keep it smooth and organic, okay? And when we get to places where we have to interpolate, just use your good judgment about how it should go through. Kind of interpolation is you guessing what you think the data is going to do, but you're not making it up. You're trying to be smooth about it. Notice I'm making a best fit line through the points. And here I've got to interpolate not only through these gaps behind Jupiter, at least I have a target window, but the cloudy skies could honestly be anywhere. But I suspect the data would have continued like that. That's called interpolation. And this is our graph from which we are.
Mine goes on to another page.
Say that.
Mine goes on to another page.
Your what? Your graph?
My graph, it goes on to a next page.
I don't mind as long as you can figure it out.
All right.
So Joel, since you're the master of getting the period, how would you say we go about it here? Usually we want to use the curve rather than the points.
Well, you could go where it crosses the time stamps.
Now, what is a period on this sine? This is called a sine wave in mathematics. What is the period of the wave? Jupiter's in the middle and the moon is going back and forth in front and behind Jupiter. So what would the period be? From what to what?
So Like from
crest to crest.
We could go trough to trough. Crest to crest is a little weird because we only have one crest. My point that I was trying to make is if we want to go crossing to crossing, we should be careful because we have to go between two crossings, right? This is it going behind Jupiter. This is it in front of Jupiter. This is it behind again. I wouldn't use the behind Jupiters because we're not entirely sure where. But if you look at the front of Jupiters, we actually have pretty good intersections right there. So what I'm going to do is I'm going to take a ruler, and you should as well, and I'm going to make vertical marks. Okay, can I hold this in my chin? Here. And here.
Oh,
sorry, almost dropped it. Can you guys see how whoa, I'm
Oh,
upside down, homie. Do you see how I went from crossing to subsequent crossing to get the period? I could have gone crest trough to trough too, but this seemed easier. So let's count the days. 24 to 24, that's one day, that's 24 hours. And then let's see how well Joel did. So that's 24 hours, 26, 28, 30, 32, 34, 36, 38, 40, 42. Nicely done, Joel. A period of 42 hours is just what we expect. Let's convert that to days by dividing 42 by 24 hours per day. That's 1.75 days. Then we divide that by 365. 3 sig
what was
big.
it? 175.
1.75. Use your calculator. Calculate with me. 4.79 times 10 to the minus 3 years. How should we get A? A is the semi-major axis or the radius of orbit. Joel, are you clever enough to look at this graph and tell me where the A is?
So are we looking for A is looking for the orbit of Io around Jupiter?
A is the distance. Like if you were looking from above, if this was Jupiter from above, A would be like the radius of orbit, right?
Yeah, so it looks like from all the data points.
Yep.
Like the crests are, so west looks like it's 2.95 and east is also 2.95.
Yeah, that seems to be about as far as it goes. It could actually be a little greater at 3, but we don't know what else to choose, so we'll do 2.95. I like that. Normally, I prefer to use the curve than the data points, but we saw 2.95 several times, and we never saw greater than that. So we know it's at least got to be that. Now we have to convert it by, let's see here. If that's in Jupiter diameters, we have to multiply by 9.545 times 10 to the minus 4. That'll convert to AUs. So 2.95 times 9.545 exp negative 4. 3 sig figs is 2.82 times 10 to the minus 3.
Oh, it's blurry.
Sorry. I did that kind of badly. I didn't leave myself enough room. So I had to put the times 10 to the minus 3 down there. Sorry.
All right, I got it.
Great. Now we've done the data collection. We've done the graphical analysis. And now we're going to attempt mathematical analysis. Because Jake's dying to go outside and play in the 30-degree weather, I'm trying to go quickly here, so I don't want to go too fast for you, but see if you can keep up with me, and please try to do the calculations here. I'm going to put this back on the tape because it's the best I can do. I'm going to sharpen my pencil.
Hey, Brendan.
Yeah.
Since my printer's broken, I just wrote out everything, like the table, the chart, and the graph.
I like it.
Yeah, I freehanded mine.
Okay.
So,
It'll always
as
be
long
nice
as you
to-
can like read it and you're okay with it.
Yeah, I feel like if you participated in a journey with me, then that's still learning. And of course, it's always fun to see how well your artistic integrity holds up there. It'll be nice to see the quality of your creativity. But yes, that's fine, guys.
Okay, thank you.
All right. So remember that if we use the weird Keplerian version of Newton's version of Kepler's third law, the mass of Jupiter in solar mass units is a cubed over p squared, but we have to use AU in years. So from our other page, the values that we got were 2.82 times 10 to the negative 3 AU, and that's all going to be cubed, divided by the period 4.79 times 10 to the negative 3 years squared. So write that down and then we're going to punch it up. Here we go. 2.82 exp negative 3 shift cube divided by 4.79 exp negative 3, and that's got to be squared, equals 9.77 times 10 to the minus 4. Now that looks like a pretty weird number for the mass of the Jupiter, but remember this is in solar mass units, which kind of makes sense, right? Because I know that Jupiter is roughly 1,000th the mass of the sun, and 9.7 times 10 to the minus 4 is wicked close to about 10 to the minus 3 solar mass units. It's very 9.7 times 10 to the minus 4 is close to 1 times 10 to the negative 3. But that's not a real value. That's just showing you that it's close enough. So the mass of Jupiter that we're going to use down here is 9.77 times 10 to the negative 4 solar mass units. Now, they want to convert this to Earth masses by converting it to 3.0 times 10 to the minus 6. That's solar masses per Earth mass. So we'll start with our number. The mass of Jupiter, 9.77 times 10 to the minus 4 solar mass units. We're going to do dimensional analysis. We're going to multiply by a division bar. We're going to put solar mass units on the bottom, and we're going to put Earth mass units on the top. That will cancel solar mass units. Our conversion is that 1 Earth mass is 3.0 times 10 to the minus 6 solar masses. So we're going to do 9.77 exp negative 4 divide by 3.0 exp minus 6. And I get to 3 sig figs 326 Earth mass units. Now it wants us to calculate the percent error. It told us that the accepted mass, whatever that means, is 318 Earth mass units. The percent error is your value minus the true value divided by the true value. It's the absolute value. So it's just the difference over the true value. So the percent error should be 326 Earth masses minus 318 Earth masses in parentheses. And that's going to be divided by 318 Earth masses. So first I'm going to do, running out of light here.
Oh, I can't see the equation. Divided by 318. Okay, I got it.
So 326 minus 318 gives us 8 Earth masses as a percentage of 318. We have a 2.5% error if we multiply it by 100. So that's 0.025. Fudge. If you multiply by 100%, 2.5% error is not bad. Cross out number 4. We don't have to do that one. And that, friends, concludes today's astounding lab on the mass of Jupiter. Got a bit darker outside, so let's see here.
How much snow did you get, Jake?
We got about like 3.5, 4 inches.
No kidding. You got snow on the ground?
Oh yeah, it's still here. Everything's like ice.
Remember, we talked about albedos, right? And it's warmer in the city. You can see not a drop of snow downtown.
Oh wow.
Yeah. So it all melted here pretty quick. And that's reflection. That's reflection of the lack of reflection, the lower albedo of the blacktop in the cities versus the countryside, right, Jake?
Absolutely.
Remember we learned about albedo when we studied the atmosphere? Yeah.
Oh.
Yeah.
Cam needed to see number 3.
Sorry?
Cam needed to see number 3. Yeah.
It's always better if you guys talk rather than type, but that's the whole bloody page.
Oh, he got it.
Okay. So you'll turn in this page. You'll turn in your graph. You'll turn in your data table. Those 3 pages are all you need. Sound good, class?
Sounds good.
Yep.
Okay, I'll work on getting those last week's work graded. Remember, everyone show up to class on Wednesday because that's your last class. We will do a homework that day. Think of it as you're doing a problem set, but you're not doing the exam. That sounds like a good trade-off to me, doesn't it? Okay.
Oh, God.
Yep.
So, okay, one more class to go. It'll be a good one. We're going to learn about Jovian moons. It'll be real fun.
Sounds good.
Okay, guys, take care of yourselves. Stay warm. Stay safe.
Jake's so excited.
I am, honestly.
Oh, bye, Greg. Thanks, Greg.